Okay, so hello everyone. My name is Andrea. I'm a former lecturer in mathematics at the University of Bath and visiting researcher at the Alan Turing Institute. And together with Zach, who is a Turing Research Fellow, and unfortunately is not here with us today because of other professional commitments, we are the organizers of a physics and machine learning meets engineering seminar series, which is hosted virtually at the Alan Turing Institute. For those of you who don't know, the Alan Turing Institute is the UK National Institute for Data Science and Artificial Intelligence. Today, the speaker at our seminar series is like one of our most welcome speakers, since he was kind enough to give us 2 more talks in the past. And he's Professor Cristian Axenie, who I'm going to introduce just now. So after earning his PhD in neuroscience and robotics from Technical University of Munich in 2016, Cristian spent 1 more year as a research fellow in neuromorphic engineering in Munich before joining Huawei Research Center in Munich. Between 2017 and 2023, Cristian was staff research engineer in enterprise intelligence for cloud solutions with Huawei's largest research center outside China. At the same time, he was head of the laboratory and principal scientist at the OD Ingolstadt laboratory at the Technical University of Ingolstadt, a Sino-German research initiative focused on human-centered artificial intelligence. Since April 2023, Cristian is now professor of artificial intelligence for heterogeneous sensors data and research group leader of SPICES Lab at the Technical University of Nuremberg in Germany. So today, Cristian is going to talk us about physics-informed machine learning for robust pedestrian detection in embedded low-power systems. So without further ado, Cristian, the floor is yours. Thanks again for giving us a talk.
Thanks, Andrea. Thanks, Zach. Wherever you'll see the recording. It's always a pleasure to be here in this nice audience, and right now being able to share more about my latest research, which goes more in the direction efficient AI. Yeah? So we want to have systems which can also come up with intelligent solutions, but also with a decent energy budget. So this is why we're looking at low power system and embedding machine learning on such devices for societally relevant problems, for example, like pedestrian detection day and night. As a short overview, my lab, it's going across verticals, so we tackle solutions in multiple domains, but the focus is pretty clear. We look at efficient, green, and robust low power inference on small devices typically, and we take as a main platform neuromorphic systems. So we look at systems, sensors, and computers which are inspired by biology, basically, and we try to build up solutions which benefit from the low power consumption in the direction of data fusion and closed loop control. This is just an overview over the type of work we're doing in the lab. And if you're interested, just can scan the QR code there on the slide. This is the current layout of the team. I just started in April, so I didn't have time to build up such a large team, but these 4, the 4 members there are the actual core of the SPICES lab, which comes from sensory motor processing, intelligence and control in efficient compute system. There's an acronym there, but I wanted to use something which is also easy to remember. So to go for today will be to actually present your solution, which interestingly enough is an awarded solution for green AI in a TinyML hackathon. So basically, I'll just introduce right now more technical details about the physics informed machine learning behind the solution we proposed for the hackathon. So I'll go through the goal briefly, and then we go through the technical details of the solution, what we use for sensors and algorithms, and then the performance evaluation, because we have a pretty strict criteria for performance evaluation, deployment evaluation, and actual bill of materials and costs. This was actually another dimension of our solution, which is also important to emphasize that such solutions have also not only impact because they are embedded and local, but also because they don't cost too much. Yeah? So the overall goal was to have a cost-effective and accurate solution to detect pedestrians and bikers during day and night, roadside. So basically we have on the gantry cameras mounted there, you record data, or like you capture data from the street and you want to detect pedestrians and bikers. At the end, we have to classify who's a pedestrian, who's a biker, and just discard background and cars and so on. Why? Because there's like this initiative called Vision Zero as a street safety policy to try to eliminate traffic fatalities for all transportation modes. It's an old initiative started in Sweden in '97, but then like right now, for example, San Jose Town Hall organized this hackathon. We also applied, and we came up with a solution for their own problem and their own setup there. So in other words, what I'll show you today is a solution for this problem, which has a very good energy footprint, is robust to work day and night, and the budget also from power budget, but also cash budget is efficient enough. We'll look at a system. Basically, I said we have sensors and computers. So we look at the sensing part on the right-hand side. So we have this event-based cameras. So we don't use frame-based camera. We use frameless cameras because we can only get the relevant information out of the scene without redundancy. So basically, we'll only get those actors in the scene which move, in our case, pedestrians and bikers. At the same time, this data will be natively processed on a neuromorphic computer, which is the brain chip Akita. Now, like without going too much into details, we had two approaches. The one was based on a spiking neural network, which is again, natively running on the board. And the second one, which is maybe more of an interest for us today, is the physics-informed expectations maximization, which actually got sparse input from such a camera and came up with a really nice recognition of the body parts of a pedestrian or a biker that were able to detect those traffic participants and even track them. So, just to give you a feeling from the data flow point of view, so we have the data acquisition model, so there's camera data coming out. This camera is again pretty special because it doesn't have or doesn't offer frames as output. It offers events, so individual pixels spitting out light intensity changes. Yeah, you think about it as a Doppler effect. Yeah, you can see it as a Doppler effect. Basically, you only get contours of things which change in the scene. And what, like the two directions we opted for was first the native spiking neural network to process the spikes coming from the camera. And the second approach was, again, a traditional machine learning in which we embedded the physics of the pedestrian and the bikers. So what we've done, we took the skeleton information, the kinetics, and basically the kinematics, and we embedded in the model itself. So basically, when it will come to the algorithm itself, I'll actually give you the intuition where physics come from, where physics comes in the model, and how this model actually was able to be run on an embedded platform on this Raspberry Pi with brain chip Akita. Well, let's clear up some details because I talked about this camera. Well, if you want more details, you can just read on the left side. It's like an embedded camera, which has this nice functional approach in which you only get events out of the camera. So basically, you don't get frames, you don't get pictures as in a normal clock CMOS sensor where you just read all the pixels and send out an image. But now each pixel reacts independently. So basically, there's a threshold there for light intensity. And when the logarithmic change in light intensity goes over the threshold, you basically have an on output, and then you have an off when you go underneath the threshold. So it's basically an impulse or spiking based camera. It's similar, or it's inspired by the way our retinas work. And this is why we also get like the data representation reduced to something which is relevant, but at the same time, this is an analog chip. So you basically also get the gain of analog electronics. So in terms of power reduction. And at the end of the day, we'll see that the overall budget, energy budget of the system actually had to gain from this choice of sensors. And we acquired multiple data sets. So we took day and night to multiple crossroads in Nuremberg and also in Munich at night, because we wanted to demonstrate also the robustness day and night. And now to give you a feeling, so on the left-hand side, you have a depiction of the visual scene with the output of the camera. Green codes for those pixels where the light intensity goes over the threshold, basically becoming active, on, and red is the opposite, becoming off. And as you see, what I said, it's a Doppler-like camera, because you see actually the contour of the person moving. But interestingly enough, you see at the beginning, the lady starts moving already in a red dress, but then she stops at a stoplight, at a pedestrian cross. Basically, she's not moving, so she's not generating any events anymore. Whereas the other pedestrians and cars are generating events. So what we want to use is this sparse representation and just only get the things which move out of the scene. Yeah, just like to give you an understanding about how this sensor works, this camera works. Now, if we look at the algorithms, basically we have now it all starts with the physics informed machine learning. But first, I have to clear up that what we've done, we actually got a skeleton kinematics embedded in the system. So what we thought about doing is trying to match, basically computing the likelihood that the events coming from the camera, this sparse representation, these pixel event coming out of the camera, are assigned to one of the body parts. So basically we built skeleton kinematics where we have the hands coded in blue, the trunk with the red, and then the legs with the yellow. And what both for the spiky neural network and the expectation maximization, we'll look at embedded this and computing a likelihood that a certain event belongs to one of the body parts. So it's all about likelihood estimation and basically likelihood maximization, because we wanted to figure out to which body part the single events coming in the system from the camera belong. In the first implementation, we have a ConvNet. More specifically, it's a fast objects, more objects, a FOMO neural network, which uses MobileNet V2 for those model aficionados. It's a MobileNet V2 as a base trunk model, and then we actually cut the end of it, and we actually made it like a probability map at the end, so that we can build these heat maps to describe the density of events attached to the body segments. So it's a hybrid model such that we can take this ConvNet and then turn it, quantize it in a spiky neural network running directly in spiky neurons in the brain chip Akida board, which is a neuromorphic platform. Basically, there's no von Neumann architecture there. You basically have a neuron fabric. So we have multiple neurons, like 1.2 million neurons and 10 billion synapses inside. So this network ran natively there on the hardware. As a demo, what you see here is the tracking performance, what we recorded directly on the board. Again, performance is not outstanding because basically we just had to limited time to train and constraints on the environment. But basically what we were able to do is to demonstrate that if we provide such a sparse input, such event-based input, we're still able to assign events to the body parts of the pedestrians while they were walking or they were running, or even like two pedestrians crossing next to each other. What's interesting, or what the goal of our work is not to get like 99% accuracy and having then like a huge power bill. It was more looking in direction how fast inference happens. Yeah, so basically you see like 25 hertz and so on, because basically the input was like combined such that we can actually feed it to the network at like 25 hertz. And the power consumption per inference step goes in milliwatt range. Yeah, but this is maybe not really interesting. What I'll show you in a second when we go to the performance evaluation, we'll have the world power, basically the whole integrated system with camera and processor, or like camera and computer, to see overall power consumption or overall power budget. So this was the spiky neural network performance. The second approach that we looked at is more a la traditional machine learning, basically an expectation maximization that we actually kind of hacked around to embed this physics, so to embed this prediction model of how this body segments change position, how each incoming event from the camera is assigned to one of these body segments. Yeah. Okay. For those who really want to get more details, this was basically a ridge regression on the squared error matrix to the delta to the change in angles. And then we had like a moving, so because this runs in real time. So we had a moving average of square distances to the segments of the events. And we calculate the squared error matrix of each source, basically the upper body, middle body, and lower body. And then we perform the regularized least square. So it's all about 600 lines of C code, which were able to implement this physics into the classical expectation maximization. Right now, done under the constraint that this would run in real time in a small embedded platform. And the whole idea is that you want to maximize the likelihood of membership to each of the body parts. Interestingly enough, as you see here, you have the ground truth in the back, you have the events input here, and in a second you'll see right now, you'll see the tracker started. What happens right now, each individual events are fed in the expectation maximization algorithm, which actually then maps and colors in the right tracker visualizer. You actually see the mapping of the incoming events to one of the body part, coded with blue for upper body, red for trunk, and yellow for legs. And this actually like describes how the algorithm works. Yeah, so you get raw input, event input from the camera, and then you actually feed it to the expectation maximization running on the embedded board, and you get this really nice tracking of or membership to the body parts. Yeah. Okay, this is the technology, or these are the algorithms and how physics was embedded. So basically, again, punchline, we got the body kinematics embedded there with all the angles and the motion generated by the body parts. This came in the model, and we looked at how the input data actually maps, translated likelihood maximization on one of the body parts. Yeah, this is the kind of like the take-home message of the talk. When we look at the performance, yeah, we saw that there were like markers jumping here and there, 2 markers per person, upper body, lower body. So basically where the hands connect to the trunk and the legs connect to the trunk. The quantitative evaluation showing us, okay, we can like have like good-ish bicyclist detection and better pedestrian with 93.8 accuracy. So again, not super like awesome or like super like 99% whatever. What super comes in 2 slides. Yeah, so we're still able to get good-ish performance with a really impressive energy budget. This is the spiking neural network performance. Again, you'll see this performance way better because basically we use the mobile net, which is a convnet, and then we just hack the lower part or like the output part of the network to make it fit in our type of data in the physics model we built in. The event-based expectation maximization, it performs worse than spiking neural network. Okay, we get like 84% bicyclist, like this is the confusion matrix, 84% accuracy in the bicyclist detection and 83 in the pedestrian. So not that fancy, but the point was this was running purely event-based in real time. And this is pretty impressive because basically you don't do so bad, yeah, in terms of performance, but you have everything running on a small microcontroller. And now the cool part comes in this slide, where we actually measured the power, the power consumption, yeah? The wall power. Basically, you have the system here on the lower, like left side. You see the board is here. We have the camera. Because we couldn't test currents and like power outside, we actually put a huge screen in front of the camera, and the camera was seeing the same thing we'd have seen on the street. Because we had ground truth, so we recorded the movies, and then we replayed it for the camera and measured power. Yeah. Again, people might say, yeah, but you don't have the same lighting conditions like outside. Well, the event-based camera has a really high dynamic range, 140 decibels. So basically, you don't really care if it's dawn or if it's the light conditions are changing, because the robustness of the camera actually solves this problem. And the sparse output still there and can still like be fed to the algorithm. The cool part was here, basically. So we had like an average power consumption of 5 watt of the overall system. So you can take the system and put it on the gantry. We actually went with it on the street, and it would just use 5 watt in the operation of the algorithm. So again, the algorithm was in taking events from the camera, like putting inside through the physics embedded inside in the model, and then actually making predictions on is it the pedestrian or a biker, or tracking the pedestrian when we look at expectation maximization. Yeah, there was a marginal difference between the two of them, so it's 5 watt to 7 watt. Well, same range, yeah, 7 watt to 5 watt. It's still marginal difference. But the cool part is that we're able to actually have, like, this is the selling point of the story. So we embed physics to help the algorithm converge faster, or like give a plausible outcome to the sensing part, where we actually get this sparse representation, and then with a really good energy budget. Yeah, because this is a fun part, because we also thought about, like, putting on a street, we had to have weatherization operation analysis. Well, we took the system and put it in an oven. So what happens right now, we don't have the input because we couldn't put a TV in the oven as well. So what we had the camera looking at a rotating fan of the oven, and then we generate enough events for the camera to get input. Yeah. Again, we don't look at the output of the prediction or of the classification, because it's nonsense. Yeah. In this case, you don't have anything coming out. But the point was that how does the power consumption change with respect to the heating of the environment, and also how the performance changes with respect to the input. So you have a lot of inputs, so a lot of events coming in the system, in the algorithms, and the system was somewhere in a really, really high temperature environment.
Can I ask
yeah,
quick
please.
question, Cristian?
Sure.
So I'm not sure if I missed this, but did you try with different camera resolutions? So maybe, I don't know, there is I mean, probably there is more energy consumption, but at the same time, you have a maybe better accuracy. I don't know if you played with that, with this parameter also.
Yeah, this is a really good point. Basically, I'll show you at the end when we did some back of the envelope calculation with respect to state of the art, which uses high resolution cameras, but the pipeline itself, it's a bit different, yeah, because you use typical frames. I would say, yes, if we increase or take a sensor like this event-based camera and have a higher resolution, then also the amount of data coming out is higher, yeah? And then, again, you have a finer discrimination. But in this case, as I said, for our task was pretty simple, because physics helps us. And I would say the physics model actually helped us solve the problem with the low resolution of the camera. Yeah. So instead of having a high resolution camera, we had a low resolution camera, but the physics model helped us to kind of split this body segments, and then the algorithm itself just made this membership allocation to out of the body segments. But yes,
yeah, because in some sense, maybe the low resolution camera really acts as a filter on the noise somehow.
That's true. That's true. It's extremely valid point. Yeah. So the low resolution acts as a filter because you don't capture so much of the scene. But actually, we try with higher resolution camera, like the HD version of the same camera. So we had like 1080 pixels. Yeah. So it's also still in the range of, let's put it this way, bytes per second throughput, but it doesn't reach megabyte level, which you typically get, or like tens of megabytes or hundreds of megabytes, which you typically get from HD CMOS cameras. But it's a really good point. Because for us was also the thing of, okay, how much does a solution like that cost? Because sounds good. You can embed physics. You can leverage out the fact that you have a low resolution, but you have the model, so you can actually gain from that. There are like the two possibilities. So you can have a worse price when you buy the commercially off-the-shelf camera, which is, again, something which goes like around thousands of euros, basically. But then, because these cameras are still like ramping up right now in the industry, but there's a huge there's an effort programming them and applying traditional machine vision on this output. Yeah, as you've seen, there are asynchronous events coming out. Yeah, so there's no way of, or like if you start framing, then you just lose the advantages of the a really high temporal resolution in reaction. Yeah, but there are also smart, like cheaper versions. For example, if you look at Samsung, they actually got a license to produce similar cameras, but they were like not rugged for the outdoor environment. Yeah, so basically you can also opt for a good price of such system when you look at like the overall setup. We have a camera and the processing unit. Yeah, this is maybe just like also to raise awareness in the community that they're like, you can still do like you still run intelligent algorithms also on platforms which natively run neural networks, not in the traditional connectionist models, but in the spiking domain. So then we can also gain from the energy point of view. I will wrap up right now because, well, it was more of a awareness talk in which I wanted to share with the community the fact that you can embed physics in neural networks or in traditional machine learning models to the point of actually having efficient learning and inference at the edge. So basically on small devices running there on the street. Yeah. So which the energy budget and scalability is an important point. So to wrap up, this is a tiny ML solution, so a tiny machine learning solution to support pedestrian detection and uses low power neuromorphic sensing and processing. And I made here like a bit of, again, back of the envelope calculation about the gain we can get. So we get like 100-fold power reduction with respect to a system, for example, a high resolution camera, which still has to have additional devices, for example, to make it also work at night or in bad light conditions when it's cloudy or whenever it's snowing and so on, or in extreme sun, basically to kind of make sure the dynamic range is also captured. The system employs only local processing. So what you've seen there, both of the algorithms were running on the embedded board you've seen in one of the pictures. Yeah, so the board was there. It takes like around watt power, like 5 to 7 watt power for the two algorithms. But the cool part is that the data with like local data, the amount of data that camera typically provides is like around 30 megs per second, like a normal frame-based camera, whereas such event-based cameras go in the range of bytes per second. Yeah, so you get like a really high gain in the data amount being transmitted, if necessary to be transmitted out. And I would say provides good accuracy. Again, good, you've seen the accuracy numbers. But what we actually gain robust visual detection. Basically, we're able to run day and night or like bad weather conditions as well. And we actually tested in day and night scenarios and provided pretty decent results. And to sum up, this is the solution we proposed for embedding physics in machine learning. So we got the human body skeleton, and then we used the sparse representation from a neuromorphic camera and embedded that in a classical algorithm. I took away the neural network for the sake of actually emphasizing the benefits of actually embedding this prior we have about the motion of pedestrians or the bikers, and basically that we can only use the relevant data from the scene and compute such spatio-temporal dynamics, because all these events have also the time dimension behind, and you can do a really interesting and fast detection of moving traffic participants, in our case pedestrians and bikers. And of course the performance looks at the detection speed, the energy budget, and the data communication if you need to send data out. So basically the amount of data produced by the system. Excellent. So this was my talk. Okay. So I wanted to just like kind of show that we can do phi-ML also at the edge, and not only with large amounts of energy and on big devices and embedding complex physics, but you can also embed simple physics of motion like kinematics, and then use this together with machine learning to actually detect and track moving objects in a visual scene in a robust way.
Okay, no, so thank you so much for the talk. Is there any question from the audience? Maybe I can start breaking the ice. So, well, I really hope that this technology, for instance, can improve pedestrian detection, like for self-driving cars. Like I read a piece of news where, I don't know, there was another accident between a pedestrian and an autonomous vehicle. So I was wondering, can you extend this approach to track the movement of crowds, for instance?
So this approach can be used also for movement of crowds. Basically, we have right now a project which looks like at crowd monitoring. Yeah, there we don't embed the physics of a single person, but we embed the motion physics of masses. Just think about it. You have only this sparse representation of moving objects. Yeah. So whatever people like, I don't know, there's people in motion. They are basically people have edges. People have edges and they have like round portions of their bodies, and everything to their motion will generate events. So we can then go into clustering mechanism to actually cluster all the events coming from a homogeneous crowd and then track their dynamics. And interestingly enough, what happens is that we can also, as I also point here, the spatio-temporal dynamics. So we have the pixel dynamics in the field of the camera, but then each pixel has also a time when the pixel actually triggered or was active. So we can extrude, if this is a good word to put it, we can extrude in time also the dynamics. So basically you have like a continuum, space and time of how those pixels change. In our case, for crowd monitoring and like anomalous event detection, for example, is a really interesting tool because this can run locally and you don't have to have centralized processing and so on, because it runs efficiently on such local embedded system, basically extending the principle we had here as well. And then the physics, you can embed whatever dynamics you want, you know, in a 2D plane or whatever.
Yeah, I mean, this reminds me a little of a project that was developed at my undergraduate university, which was called star flagging, which like people were studying the dynamics of flock of birds or also other animals, of course, from a different perspective, because back then, like there was not such a huge interest in machine learning. But yeah, maybe I can share with you the link later on. So are there more questions from the audience? Like, if not, like I know, Cristian, that you have another talk in half an hour, so maybe you can take a break between.
Yeah, no worries. I just, now that I have the chance, I could also like, there's a chat, there's something in the chat, so I think maybe there is a question.
Is Passage Lab a reference to Dune?
A bit. It's a bit, because like, good question. Yeah, it is a bit. It is a bit. Yeah, I'm a big fan of Dune and this kind of literature.
Well, it could have been a reference to the Spice Girls, just a UK reference.
Yeah, a UK reference. Yeah, guys, I think Spice Girls just started when I was a kid, I guess, myself. So I'm not that old. Yeah. I have a question from Hamza. Thanks, Marcus. This is a good question. In terms of the implementation, what does the sparse representation look like? Is it the matrix with the pixel that change in the camera's elements in the matrix? Oh yeah. So this is actually a fantastic question. So the camera itself, the chip itself, provides asynchronous pixel output. So imagine that you in your camera array, you have, I don't know, in this case, 128 by 128 pixel, and each pixel has this threshold set. When logarithmic light intensity changes, goes over the threshold, the pixel becomes actually sends out something like a timestamp when this pixel actually was active, the location in XY, so basically in width, height of the camera, and the polarity, on or off. So this is the whole information a pixel sends out whenever it becomes active. And why do I say it's sparse? Because pixels react independently. Pixels are asynchronous. And the circuitry there is analog. So there's no sample and hold, there's no clock to read out. Each pixel reacts independently. We also make sometimes in the field this analogy that basically if we go to nanosecond time resolution. So you basically have a really sensitive pixel, nanosecond time resolution. And then actually you go in gigahertz number of frames. Yeah. So you can have millions or even more frames per second. Yeah. And pre-processing, there's none. So basically, in the expectation maximization part, where we actually infuse the physics, we had per event processing. So in other words, how each event contributes to the improvement of the likelihood, or computing the likelihood of this event to one of the segments. We basically build the estimate of the position of the human subject. Yeah. So this was the actual really interesting contribution, that we extended expectation maximization in a purely event-based manner. So basically each pixel contributed to the estimate. Yeah? So there was no pre-processing done there as well. For the spiking net, fair enough, there was a small aggregation because the mobile net actually, like all other mobile nets and YOLOs, you need frames to fit it in. Yeah? It's a common, sorry. So there is like a post-processing that we have to aggregate events. Thanks a lot, Hamza. Really good question. Tiago, can you somehow calculate the speed of pedestrians or location? Oh yeah, this is actually closing the loop for traffic control. Really a good question. Yes, we can compute the speed of the pedestrians. How? Using optic flow, or basically one thing would be optic flow and event-based optic flow. Yeah, basically we actually see where the direction of motion is, and we can calculate optic flow given that the camera is calibrated. Yeah, so we have to have calibrated cameras basically to know how fast, or like how does the velocity of a pedestrian or an object moving maps to the velocity of the object on the frame. Yeah, so camera calibration, highly important. But theoretically, yes, we actually have experiments on event-based optic flow and how we can calculate velocities and also accelerations. And location, yeah, again, you need calibration because you have to map the location of the field of view of the camera to the real world location. So anyway, depending on your field of view, you have a limited amount of the perceived space. And interesting to recalculate green time to those pedestrian intersections. Fairly valid point. We had another projects where we actually try to close the loop. Yeah, basically using this information on the velocity and so on to close the loop and actually adjust the phase time, the green phase time at the traffic light. But there's a problem. As you also noticed in that animation, when the lady with the red dress stopped at the pedestrian cross, she was invisible for the camera. So we couldn't figure out, okay, there were other people and cars moving, but she stood still. So there was no event generated. So basically she was invisible for the camera. And now I'll have to mention fairly enough that if we fuse the data with a normal camera to get the context, yeah, to get the semantic of the scene, because these cameras only get the changing part, only get the dynamics. But if we have a normal camera to kind of fuse it with the event camera, then we can get context, and then you can actually have, I would say, reasonable estimates of motion to also recalculate green time. And also use this in the closed loop control of the green time allocation. If you look at my previous talk, I actually worked a lot on control of traffic, adjusting traffic lights. So just look on the self-advertisement, look on the Turing website, and you see my previous talk on control. So I have a bit of experience on how to actually use this information to close the loop with the traffic light. Hamza, another question. Thanks, Tiago. Hamza, another question. Interesting. How did you map the pixels to the things like angles and body parts? But this was the actual cool part. I will not disclose too much because we also want to publish this algorithm. But as you have there, like adding this prediction model, yeah. So basically, we took what you have there. You see the send. So basically, there is a sneak preview, yeah. So look at this. Adding a prediction model on this slide that right now is up there. So you have for each body segment, you have a change in the angle. You see each of the body segments, is why we colored them blue, red, and yellow. And what happens is that you compute an estimate of the future center. So basically what you do, you run the kinematics. So what happens is that you always based on the distinguish a second. Yeah, exactly. This is how it happens. So basically what you do, you look at the change in angles, kinematics, the change in angles, where red, blue, and yellow are the arms. And then what I also mentioned, we do ridge regression to actually calculate the distance between the events. You see in the left-hand side, have these gray dots. These gray dots are the events. So basically we look and assign them, or we try to figure out which of the segments maximizes the likelihood and expectation maximization. And this is how we allocate the events to a certain arm. And based on that, based on the body segment, then you actually have centers of the body segments based on the accumulation of events belonging to a certain body segment, the blue, the yellow, of the red, or the red. I don't want to disclose more details because principle is there. This prediction model is embedded inside the algorithm, and it works like this. So likelihood maximization of an event belonging to one of the body segments. Could it potentially distinguish? Yeah, thanks a lot, Hamza. Carlos, could it potentially distinguish between cyclists and motorbikes? Like this was the actual point, the movement of the legs. Yeah. So the angles, the theta y is the angle between the trunk and the legs. This was the actual difference there, because you can also cap the maximum value of the angles. Again, it's physics informed, so we can put all the priors we have inside a model. And this is why physics informed helped us in this case, because we don't have to have an unlimited motion, because sorry, it's not physically possible that the legs go around, so they don't wrap up. Yeah, so sorry guys, but like the thing is, you can put and we can cap the maximum value of these angles, and then make sure you distinguish between cyclists and motorbikes. Cyclists, sorry, I was initially thinking about cyclists and pedestrian, but now cyclists and motorbikes, yeah, on motorbikes, they don't move their legs and their hands. Yeah, it's just the motion of the trunk, and there's the assignment will be a bit different, because also the velocity of a motorcycle is different. Yeah, and I would say that we can make the system even more robust, combining a bit with what Tiago say, basically saying that if we also compute the velocity of the objects, then you can even make even better this prediction model embedded in the expectation maximization, because then we can cap the velocities, saying if the velocity is higher than a threshold, this is definitely not a pedestrian or a biker. So it's normal that the legs and feet don't move. It's just the overall body which moves. Yeah. So then it might be the case that the algorithm assigns all the events to the body trunk. Yeah. Good question, Carlo. Awesome. Yeah, of course, Tiago. Like, but again, the framework, we are at the beginning. Yeah. So the framework sells itself as physics infused machine learning. So we embed as much physics as we have about the problem we have at hand in a lightweight machine learning model, which can run on embedded devices. Yeah. So I would say we don't have to only think about AI as like, yeah, large language models or like big models for like discovering things in data structure or unsupervisedly extracting structure from data, but also about AI at the edge, where we work on algorithms which are destined to run on low power and resource constrained devices. Excellent questions. Thank you all. Lovely, because this is what I was also expecting. Yeah.
Okay, no, thank you so much, Cristian.
Of course.
So if there are no more questions, then okay, well, I would like again to thank our speaker, and so that you can take a break between the two seminars, and well, hopefully we're gonna have you as a speaker soon.
Let's see. Yeah, let's see the progress on this, and then definitely my pleasure to join the talk series. Yeah.
Okay, well, thanks again, everyone, and enjoy the rest of your day.
Have a nice
Bye-bye.
afternoon. Bye-bye.